So for the chapter 14 comprehension check, starting with question number 7, you need to understand the first law of thermodynamics and the second law of thermodynamics. So the first law of thermodynamics, you've probably heard some version of this since you were little, but it's that energy cannot be created nor destroyed. It can only change forms. And sometimes you'll see where it'll say can only be converted. And so what that just tells us is I'm never going to be actually, as I'm doing an experiment, energy is not just going to be disappearing or coming out of nowhere. It's either going into something or coming from something. And so then we get introduced to the second law of thermodynamics, and it tells us that the entropy of the universe can never decrease. Well, what is entropy? This is probably the first time you're hearing this term of entropy. So entropy is the potential energy that is in a chemical reaction that does not have the ability to do any work. It's energy that is in the compound or in the reaction, but it's not actually doing anything. And so the entropy is kind of makes it random and just disorder. So sometimes people will describe entropy as randomness or disorder in a reaction. And so what the second law is telling me is that the entropy, which is this randomness and disorder of the entire universe, will never be decreasing. It's always going to be either staying the same or increasing. Now, this law refers to the entire universe. It does not refer to any specific reaction that you'll be doing. So question number 7 refers to a lab that you did in the book. So the lab that you did in the book is a calorimetry reaction, and where you basically are doing a reaction inside it that releases heat. And as the reaction is releasing heat, we're assuming that all the heat is going either into the water or into the calorimeter itself. So the question asks, which law of thermodynamics are you using to make the assumption? The assumption is that all the heat from the reaction either goes into the water or into the calorimeter. And so the law that you're actually using to make that assumption is the one that says energy cannot be created nor destroyed. As the reaction is producing energy, it has to go somewhere, and so it gets absorbed either into the water or into the calorimeter. And that is the changing forms or being converted. Question number 8 gives you 3 parts, and in each of the parts you have 2 scenarios. And the question is asking in which of the scenarios is the entropy the highest. And so entropy is energy that isn't being used, and it's like randomness and disorder into a system. And so in order to figure out what that is, we're just going to have to think about, let's think of temperature. At a higher temperature, a compound has a lot more energy and a lot more disorder because the molecules are moving a lot more. So entropy is higher at a higher temperature. Also, the more molecules you have, the more disorder you have. It's like kids in a room, right? The more kids you have, the more crazy it's gonna be. And the other thing you can think about is in space. So if you have a gas and you take those molecules and you put them in a large volume, they have the ability to move around a lot more. And so you're gonna have a lot more randomness and disorder. And you can kind of think of a classroom of students also. If you take a classroom of students and you put them in a small space, they're probably gonna all just have to sit still because there's not a lot of space for them to be crazy. But if you took that same group of students and you put them in a gymnasium, they would move around a lot more, and so there would be a lot more disorder and randomness and a higher entropy. So for question A, it tells us we have 100 molecules at 100 degrees Celsius, or we have 200 molecules at 200 degrees Celsius. So more random and disorder is going to happen at a higher temperature, because a higher temperature is more energy, and it's going to also happen with more molecules. Just the more molecules you have going on, the more randomness is going to be going. So B, each part we have 1 mole, and we have 1 mole of water vapor at 100 degrees Celsius, and we have 1 mole of liquid water at 100 degrees Celsius. So both of these contain 1 mole and are both at 100 degrees Celsius. So the difference is one is a water vapor and one is a liquid. And I hope you understand at this point that a vapor or a gas has way more energy in it. The molecules are bouncing around a lot more. And so there's going to be a lot more entropy in that system. All right, so the third part tells me I have 500 molecules of gas in 1 liter. or I have 500 molecules of gas in 2 liters. And it goes on, I didn't write it down to say that they're at the same temperature. And so if they are actually the same amount of molecules at the same temperature, but they're in different size vessels. So we have one where they're combined tight to 1 liter, but when the 2 liter one, the gas molecules are able to bounce around and move around and have a lot more space. So there's going to be a lot more randomness and craziness in that one. All right, question number 9 tells us that some creationists actually believe that the second law of dynamics would forbid evolution from happening because evolution requires an increase in the complexity of an organism, which decreases an organism's entropy. And it says, based on what you've just learned, what's wrong with the argument? I'm going to use my kids' magnets to try to show you an example of this. And so what evolution would say is that we have all these random parts and there is a lot of disorder going on here. So we have a lot of entropy. And so what the argument is saying is that if we move through evolution, try to make an owl or a bird or something, but through evolution, if our disorder was able to organize itself, then we get into very complex animals and things. Now, the problem with this, with the second law of thermodynamics is, yes, the second law of thermodynamics says that the entropy cannot be decreasing. Well, in here, my entropy is decreasing. I have less disorder. But the law says for the entire universe. So the whole universe disorder cannot be decreasing, but it can be in different situations and in different scenarios. So that's not a very good argument. So question number 10 asks you to find the delta S, the sign of the delta S for several different reactions. And so delta S is what we were just talking about. It's the symbol that we use for entropy. So it looks like this, triangle S. And S is used for entropy. I know it sounds weird to use an S for entropy, but we've already got E used throughout, so you started using S. What we're going to be doing is we're going to be looking at these situations and trying to decide if the entropy is either increasing or decreasing. And so if it's decreasing, it's going to be less than 0. And if it's increasing, it's going to be greater than 0 or positive. We're going to be doing similar to what we just did, question number 8, except this time it's given to us in a chemical reaction. So let's look and see what's happening. So I have 2 compounds in the gaseous phase, and they're actually going to be one compound in the gas phase. So the phases aren't changing, so I can't look at that to tell what's going on with the amount of entropy. But I can say that here I have 1, and then there's 1 nitrogen and 3 hydrogens. So there is a total on the reactant side of 4 molecules. And so 4 molecules in the gas phase, and on the other side, I have 2 molecules in the gas phase. And I know that 4 molecules are going to have a lot more entropy or disorder than are 2. So actually the entropy is getting less. So it's going down. It's like, say you have a crazy room full of 4 kids and you get rid of 2 of them, you've lost half of your craziness. And so we would say the delta S is less than 0 or negative. That would be a way of writing that. So let's look at this equation. We have calcium oxide and reacting it with carbon dioxide, and it's going to make calcium carbonate. So let's look at the phases. So we have a solid and a gas, and it's going to be a solid. So don't have all phases are not the same. And so I know that a gas has more entropy in it than a solid. But let's also look at the number of molecules. So in the reactants, we have 1 molecule and 2 molecules. We have 2 molecules, and it's going to 1 molecules. So over here we have more molecules and a gas phase, where here we have 1 molecule in a solid phase. So the entropy is going to be decreasing because there's less craziness going on in 1 molecule in the solid phase. So the delta S is less than 0. Now remember with these, how we just talked about how even though the second law of thermodynamics says that entropy cannot be decreasing in the universe, it can be decreasing in individual situations. Just the total entropy in the universe cannot be going down. So the last one we have a very much longer reaction. So let's look at the phases. We have a solid and a liquid, and then it's going to be in a solid and two gases. So I automatically know two gases are going to have a lot more entropy than one solid and a liquid. And let's look though also at the number of molecules just to double check. So this one we have 2 molecules plus 2. So in the reactants you have 4 molecules, and in the product you have 4, 5, 6, 7. So not only do I have a solid going to a gas, but I have 4 molecules going to 7 molecules. So I'm going to have more randomness with 7 gas molecules than I do in the reactants. And so the entropy for this one is getting bigger. So it's going to be delta S is going to be greater than 0. So like in question number 10, we were able to determine if delta S is a positive or a negative, or if the entropy is increasing or decreasing. It actually is helpful to have an actual value that you've attached to that. And so we're going to get a new law that's going to teach you how to calculate values for delta S or entropies of a reaction. So I've added it up here. No, this is very confusing looking, but the top part is just a simple reaction where I have 2 reactants, and the little b is just the number of moles, and it's producing 2 products where you have the little c is the number of moles and the c is like the actual compound. And so below it immediately I have the equation for Hess's law for delta H that you just used in the last part of the chapter. So we're going to add on to this a new equation for delta S. Now the equation for figuring out entropies is almost identical for Hess's law. So that's why I've tried to keep the same colors. So it is almost identical. So you're basically going to have the number of moles of the products times a constant. And so you add this up for all the products, and then you're going to take it away and subtract it for the reactants, which is very similar to what we just did for figuring out delta H or enthalpy. Now, the only difference is that for this one, you actually use a formation constant that has an S with the degrees. And so just like with enthalpy, the degree symbol just means that this has already been done in a lab, and it has actually been done at 25 degrees Celsius or 298.15 degrees Kelvin. Remember, we do that because that's about room temperature, and that is at what most laboratories can safely and easily do experiments at. And so that just lets us know that these numbers that have already been calculated and figured out for you were done in a lab at that temperature. And so you're going to have in your textbook on page 437, and I'm going to be putting that up there on the screen for you, a table. And just like the past tables, you are not expected to memorize this table. It is there. You are welcome to use it on any of your tests coming up or any of the problems. So please do not try to memorize this table. But what this table tells us is it tells me some of the entropies that have already been calculated. And so to figure it out for a reaction, I add the entropies up for the products and I subtract the entropies for the reactants, which is almost the exact same as we did in enthalpy for Hess's law. Question number 11, they give us a formation reaction or synthesis or composition. Different books call it different things, but basically we have 2 compounds and we're adding them together to make NH3. And it wants us to calculate the entropy that happens in this experiment. And so we could actually do what we did the last time, and we can look at phases to see if this is going to be a greater than 0, a positive number, or a negative number. So if I look at the phases, I have 2 gases, and it's just going to a gas, so I can't determine it based on phases. But I can determine it based on the number of molecules. So I have 1 molecule here, and I have 3 here. So in my reactants, I actually have a total of 4 molecules, and I'm going to be making a product with 2. I keep saying kids because I have a bunch of kids in my house. But let's say I go from having 4 kids run around to only having 2 run around. My entropy is getting smaller. So you're going to be looking for a delta S that's smaller. So that would be a negative or less than 0 delta S in this equation. So let's try to use this to calculate, though, precisely instead of just saying the sign and saying, I know it's negative. So I'm going to take the first for the products. And so I only in this equation have one product. Now, even though my formula allows for 2, you could even add a 3rd or 4th in there, but they tried to simplify it. It's hard to imagine that's simplified. So we only have it for one product, and I have 2 moles of that product. So I am going to take 2 moles, that's what the little C there stands for. And then you're going to take in your chart, which I'll put up and try to highlight it, you're going to look for the amount of entropy that is found in NH3 in its gas phase. So when you look it up, you get that if you look up NH3 and make sure and remember that phases are important on this chart. There's actually 2 NH3s, so make sure you're looking for the right one. In the gas phase, it has 192.7 joules per moles kelvins. There's a little bit different units for entropy than there was for delta H, but when you line this up, moles will cancel out, and your answer will be in joules over kelvins, and that is the unit we use for entropy. So I have now done it for all my products, so I'm going to take away the entropy from the reactants. All right, so on my reactants, the first one I'm going to do is nitrogen. I have 1 mole of nitrogen, and then when I look up the entropy for the formation of nitrogen gas, I have 191.6, and moles are going to cancel out. So do it for the next reactant. So you're going to take away the next reactant. For this one, I actually have 3 moles. So I'm going to, as I take away from my 3 moles and I look up hydrogen gas, I know that hydrogen gas has a entropy of 130.6 joules per moles kelvins. Moles cancels out. And so you're going to put this through your calculator. You're going to have to use a lot of parentheses if you put it through in one motion. And so make sure that parentheses are around the multiplication parts of the problem. At negative 198 joules per Kelvin, and we're going to talk about why the Kelvin is there in the next section. And it is a negative, and I had predicted earlier that it would have a delta S of less than 0, and that is true. Before we can start into question number 12, I have to introduce you to another concept and a new formula for the chapter. There's a lot of formulas for this chapter, but this is considered called Gibbs free energy. We're going to take our formula for delta H and for delta S, and we're going to combine those into one formula to try to determine if a reaction is what we call spontaneous. And spontaneous means that the reaction will proceed. It doesn't mean it will just happen automatically on its own, but basically if I put some energy into the reaction, will the reaction then continue and not stop? And so to calculate, to determine if that will happen, I need to know the delta S, which is really dealing with the entropy of the system, right, of the reaction, and then the delta H, which tells me about the enthalpy or the heat that is going on outside of the reaction, right? And so we need to calculate both of these to figure out the Gibbs free energy, to know if a reaction is spontaneous or not. So basically it just lets us know if this reaction will happen. Will it proceed by itself without, after you give it an activation energy? And we get this formula, that's the delta G, and we need to know delta H, and you subtract the temperature times the delta S. And if we get a negative number for this, you can be sure that this reaction is what we called spontaneous. Doesn't mean it's just going to happen on its own, but once you get it going, it will proceed. If you get a positive number for this, you can calculate that this reaction is not going to proceed. And so let's look through a problem on how to do this. Question number 12 tells me I have a chemical reaction. They tell me what the delta H is of the reaction, and they also tell me what the delta S is of the reaction, or the entropy. And remember in the last problem I told you we will get to the temperature part of the entropy units, and we're about to see why we need that temperature part of the entropy units. And it tells me that this reaction is being done at 25 degrees Celsius, and the question just asked is it spontaneous? Is it going to happen? In order to calculate if the reaction is going to happen, we need to use this Gibbs free energy equation. Now, when I look at this equation here, I'm going to basically take this information and put it in here. And the only catch to this that they try to trick you on, I wish they didn't do this on the first problem, but is that the unit here is joules per Kelvin, and they tell you at 25 degrees Celsius. So we have to make sure that our temperature is in kelvins when we put it in. And so I'm looking for delta G, and I know delta H. And I'm going to subtract the temperature, which has to be in kelvins. And so 25 degrees Celsius is 298 Kelvin. So I'm going to take my 298 kelvins and I'm going to multiply it by a negative 112 joules per Kelvin. And so this is why this has to be in kelvins, is so that they will cancel out. And the other part of my units in this equation that are not right, if you'll see I have kilojoules and joules. So I need to put this into joules. I just moved my decimal, right, 3 steps. I'm using King Hair Dyed, if you can remember that. And so now I basically am going to end up with a joules minus a joules. When you put that in your calculator, I get negative 131,600 joules. And then this, because I have a temperature of negative times a negative, becomes a positive. So I'm adding a positive. And when I do that addition, you end up with negative 98,200 joules, which lets me know when delta G is negative, it's spontaneous, which means this reaction will proceed. There's a second part to question 12, and it asks you what is the temperature range at which this reaction is spontaneous. So as you're determining delta G for a reaction, you'll notice there is actually a temperature part of the equation. And so delta G changes based on the temperature. Some reactions proceed at a higher temperature as a spontaneous reaction, and as the temperature cools down, they're not, or vice versa. And so the temperature matters. And so the question is asking you, at what range is this reaction spontaneous? And so we're going to try to think about how we could solve that. So I know at a spontaneous reaction, delta G is negative or less than 0. So if I write this as an inequality, I would end up with an answer as a temperature, and solve for temperature, I'm going to get a range. So by an inequality, I mean, if I say that delta G is 0, or like this number is less than 0, then I could figure out what the temperature range was. So I'm going to solve for T. Just kind of track with me if you're really confused as what I'm doing here. Basically, the first part of the problem, we solved it using 25 degrees Celsius or 298 kelvins. Now I want to figure out what is the lowest that number can be and this reaction still go. I want to solve it this, so I know that I'm going to put in delta H from the previous problem, and remember to keep it in joules. I'm going to take away temperature, which is what I'm looking for, and I'm going to multiply that by the entropy, which is joules over Kelvin. Now, I'm going to keep solving this so that I get my answer in temperature. So the first thing I would do, oh, this is negative, sorry, is I would add this to both sides. So then you would end up with, basically, since this is negative, I'm going to add 131,000 to this side, and then I add it to this side, so that cancels out. And then to get T alone, I'm going to divide by negative 112. And that gives me the negative T. There's still that negative there. And these are not equals, this is an inequality. And so now, if I want to get rid of this negative, I'm basically just going to get rid of the negative sign that's out here. And so 131,600 divided by 112, your joules will cancel out, and you're going to be left with an answer in kelvins, which is your temperature range. And I get 1,180 kelvins. And as long as the temperature is greater than 1,180 kelvins, I can plan on this reaction being spontaneous or actually proceeding. All right, so when we get to question number 13, we're going to keep using some information we've learned from Gibbs free energy, but you actually don't have to use the equation we were just doing. This equation. There's a different way of doing it also. And so just like with Hess's law up here, delta H, and just like for the entropy law, we actually have almost the identical equation that we can use that for Gibbs free energy. I did not rewrite it, but it looks the exact same. This would be delta G, and then this would be a G like this, but with a G on it, okay? And those values come from a chart on page 444 of your textbook. And so somebody has basically done a bunch of reactions and has already calculated the Gibbs free energy for the formation of a bunch of different compounds. And so we want to figure it out for a whole reaction. We're going to take the Gibbs energy of the products, like we're going to add up with the products, and we're going to subtract the Gibbs free energy from the reactants, very similar to what we've done for entropy and for delta H. And so on the chart, it looks like this. It's the difference in Gibbs delta G for the formation of a compound. So you pick your compound, and on the chart, you have this, which just means it's the Gibbs free energy, can tell you if it's spontaneous or not. The F is just for the formation of that compound, and the degree sign once again tells me it was done at 25 degrees Celsius, just like in these other two equations. I got two choices. I can calculate this way, where I would have to calculate the delta H of the equation and the delta S at the temperature. There is nothing wrong with finding the Gibbs free energy, which basically tells me if the reaction will proceed or not, that way. But the other way that you can do it is you can use the chart on your book, and I'll put it up above so that you can see exactly what I'm talking about. And you can use that to calculate the delta G. And it's a little bit simpler because then I'm not having to calculate that. If I used this equation, I'd have to do three equations. I'd have to calculate the enthalpy, I'd have to calculate the entropy, and then I would have to calculate the delta G. That gets a little confusing, and it leaves a lot of places where you can make mistakes. So what we're going to do is we're going to use the chart, page 444, and we're going to determine whether this reaction will proceed spontaneously or not, and we're going to use a formula very similar to these two. I did not write it down because it basically would look identical, except this would be delta G and this would be a G. For the chart that we have, we can only do this if the reaction they give us happens at 25 degrees Celsius, but the question tells us we know the following chemical reaction is spontaneous at 25 degrees Celsius. So I know I can calculate it using this new way. And it wants me to give a range for delta G for sulfur dioxide. So basically, here's the equation I've got. I'm taking carbon disulfide and oxygen, and I'm reacting it, and I'm going to produce carbon dioxide and sulfur dioxide. Now, the question tells me at this temperature, I know it's spontaneous, and I'm looking for the delta G for SO2. So this problem is really hard to even figure out what they're asking. I feel like I've read it like 5 times just to know what in the world we're trying to solve. But it's asking for a range of temperatures for the delta G for SO2. And so we're going to actually solve using this type of equation for the SO2 variable. So let me just walk you through it, and hopefully that'll help it make sense. So if I'm going to say delta G equals 1 mole of CO2, and I'm going to look up CO2 gas on the chart. I'll put it above so that you can see where I get the numbers from. Okay, and for CO2, it's negative 394.4. Yes, I'm being lazy on the last problem and dropping my units. So you're going to add also the other product, which is SO2, which we don't really know. So you're going to keep the 2 moles, and you're basically going to keep the delta G for SO2 as an unknown. You're going to do the same thing for the reactant, so we're just going to subtract. So we have 1 mole of CS2, and 1 mole of CS2, and its delta G from the chart is 66.9. The other reactant I have is oxygen. Even though I have 3 moles of oxygen in its natural state, which is O2, it is 0, very much similar to delta H in the Hess's law. So it would just be 3 moles times 0, which really is 0, okay? So now I'm gonna try and simplify this as much as possible. So what I mean by that is I can go through and I can do this multiplication here. So when I work through all of this, I'm left with negative 461.3, and that's gonna be adding 2 moles of delta G of SO2, and I don't know what that is. This is a really hard problem, so don't get totally stuck on it if you don't understand it. I know that I want this reaction to be spontaneous. This reaction is spontaneous when it's less than 0, when this is going to become a negative, when this is a total negative number. So I'm going to set it and so that it's less than 0. So I'm going to add this over here, so I get 461.3 equals 2 times delta G, not equals, sorry, always forget that. Divide this by 2 so that it cancels out. Divide this by 2. I hope you're following with the algebra here. And you get, so when you divide this by 2, a delta G 230.7. The question asks for a range, and so any number that is bigger than this 230.7 would give me a delta G that is negative. That would be spontaneous. So that would be my range that the question is looking for the delta G of the SO2. Really hard problem, but you guys, we've made it through it. Don't get totally lost in this problem. I am well aware that it is a challenging one.